Okay, welcome back to Photoelectric Effect screencast number 3. And here we're going to look at the Einstein photoelectric effect equation. So in our last screencast we looked at the fact that an incoming photon will transfer its energy to an electron, and if it has enough energy, that electron will be ejected, and if it doesn't have enough energy, it won't. So Einstein, by looking at these results, realised there was actually a fairly simple relationship between the energy of our incoming photon and the energy of our ejected photoelectron, and that was the following. Basically, he realised that the kinetic energy of the ejected electron, so we're going to call that a photoelectron, was equal to the energy of our incoming photon. So here's our photon, and it's coming in, it's going to strike that electron. So it's equal to the energy of our photon, which is HF, I might go for a different blue there, I think. So there's the energy of our photon, HF. So the kinetic energy of our photoelectron will be HF, but some of that energy is used simply to get the electron out of the metal. And that energy, remember that minimum energy needed to get the electron out of the metal is called the work function. And so it's going to be HF minus W. And that's the photoelectric effect equation, where HF is the energy of our photon and W is the work function. Now, one thing that you perhaps need to know, or a number of things you need to know, but one thing certainly is that you need to be consistent with your units. So if you're operating in electron volts with your work function, then that compels you to then use the electron volt version of Planck's constant, and your kinetic energy of your photoelectron will be in electron volts. So either use electron volts throughout the entire equation or use joules. It's one or the other. You cannot combine them in the same calculation. So if some of your information is in joules, you're going to have to convert it to electron volts and vice versa. By the way, let's just make sure we know how to do that conversion. So to convert electron volts to joules, you will simply multiply by 1.6 times 10 to the negative 19. Now that's to convert electron volts to joules. To go back the other way, of course, you would divide. So if we're going to go this way, joules to electron volts, we're going to divide by 1.6 times 10 to the negative 19. And so it's a pretty simple matter to go from one to the other. Remember, they are both units of energy. Both of them are units of energy. And you might also notice that if we're typically looking at energy of photoelectrons or electrons or photons even, often they'll have rather small values if we're looking at it in joules, but if we're looking at electron volts, there'll be numbers like 2.3 or 4.3, which is suggesting the electron volt is a more appropriate, easier unit to deal with when looking at things at this scale. So that's one of the reasons why the electron volt is in fact used quite predominantly when looking at atomic phenomena. Okay, so we'll just basically finish this up, this screencast up by pursuing that calculation we thought about earlier? Remember in the previous screencast I challenged you to work out the frequency or wavelength of a photon that would knock an electron out of zinc. So let's have a look how we could use this equation to work this out. So let's have a look at our information. We know that in this case we're dealing with zinc, and so we know that the work function is going to be 4.3 electron volts. Okay, now if we want the minimum kinetic energy, if we want the minimum frequency necessary to knock the electron out, what we're trying to do then is just get the electron out, just out of the metal, but it will have no kinetic energy. So we just want to know what is the lowest frequency that would just get that electron away from the metal, but give it no excess energy. So under those circumstances, the kinetic energy of our photoelectron will be 0. So we can now work out what that frequency would be. So we will simplify this equation, and it's going to be 0 equals h f. Now, this f we're working out is a very special frequency. It's called the threshold frequency, the minimum frequency that can knock an electron out of the metal. So it's got a special subscript, f0. That's called the threshold frequency. Minus w, well in this case we know that w is 4.3. So there's our little equation. So in other words, hf0 equals 4.3. And we're working in electron volts, and so f0 will equal 4.3 divided by Planck's constant in electron volt seconds. So that will be 4.14 times 10 to the negative 15. And if we perform that calculation, we find that we've got 4.3 divided by 4.14 exponent negative 15, and that ends up equaling 1.04 times 10 to the 15. 1.04 times 10 to the power of 15 hertz. And that, I am fairly certain, is in the UV part of the spectrum. Okay, so that's one example of how we can use the Einstein photoelectric effect equation to do a calculation. And in the remaining 2 or 3 screencasts, we're going to do different samples of calculations and look at what happens when we try different frequencies of light. And finally, we'll look at how we can interpret this information and graph these results to get a general picture of what's going on with the photoelectric effect. Okay, so thanks for listening, and hope to see you on screencast 4. Thank you.